Welcome to Introduction to Data Visualization, Part 1, Decoding. I'm Kendra Edig, and I'm a fifth-year PhD student at J.B. Pauline's lab at McGill University. The important division here is between encoding and decoding. Decoding happens when someone sees your figure and understands something about your data. Encoding happens when you write code to create the figure according to your plan. In these lectures, I hope you will learn to use the principles of encoding and decoding to efficiently create visualizations that are effective and reproducible. Understanding decoding will help you create visualizations that are more effective, and understanding encoding will help you make figures more reproducibly and efficiently. In this lecture, we'll talk about decoding, and this is our outline. In order to plan an effective visualization, we need to think about the message, that is, what we want to communicate, perception, how best to communicate it, conventions, how it's usually communicated, and the context where it will be seen. First, we'll talk about what we want to communicate. It's important to remember that while raw data has no inherent message, a visualization does. Your design choices display, hide, and emphasize different parts of the data. Once we know our particular message, it's helpful to abstract it. Say we want to show that there are more males than females in science. Essentially, we want to show a difference between magnitudes. Alternatively, say we want to show that certain brain areas activate together. Essentially, what we want to show is a grouping or a pattern, and maybe the exact values are not as important. So this abstracting will tell us how best to visualize our data. Now we'll talk about the best way to communicate the message based on psychophysical evidence. In case you're not familiar with psychophysical experiments, let's do a little demo. Which blue bar do you think is taller? What about now? And what about now? You can see that alignment and proximity are important for judging two magnitudes in this way. Let's do another demo. Which square is 2 times as large as the black square, the pink one or the green one? Now guess which dot is 2 times as high as the black one, the pink one or the green one? And now guess the same thing. You can see with these annotations that in each case the green element is 2 times higher than or larger than the black one, and the pink one is 2.5 times the black one. But it's much easier to see this on the aligned scale, which is what we have here on the right. Here's a figure showing the results of an experiment where they had people do something like what you did. On the x-axis we have the error rates. There are more errors as we move to the right. They've also redundantly encoded this error rate by ordering the chart types by their error rate. This makes it easier to see the message, that is, to see which charts are more accurately decoded. You can see through this ordering that positions up here elicit fewer errors than chart types that rely on angles or areas. Remember this example? The previous slides showed that certain visualizations are better for decoding magnitudes. Now we're going to talk about color, which is important for visualizing things like patterns, shapes, and contours. First, let's do a demo again. Which box is 2 times lighter than the left box? Here are the exact values, the exact ratios. And even with the scale, it's hard to decode the exact magnitudes. Here we have a plot showing a model of what we just experienced. It's a plot of the physical intensity of a stimulus and the corresponding perceived sensation. You can see that length here in purple is a straight line. It has a linear relationship between the physical intensity and the perceived sensation. So that means if you make something 2 times as long, we can decode accurately that it's 2 times as long, as we just showed in some of the previous demos. For something like brightness, though, the relationship is nonlinear. We see that in gray here. We would need to square the physical intensity in order to get a matching sensation. So let's dive deeper into color. It's a very salient cue, very eye-catching, like these adorable little hummingbirds here, but it's very complicated. When most people talk about color, they use color names. It's most obvious that each part of this circle is a different color. This property is called hue. But there are also differences in luminance or lightness as we go around this circle. This is a less conscious cue than hue, but it's important subconsciously for letting us decode shapes and edges. Let's explore how this is relevant to data visualization. Named colors don't work very well for representing ordered data. These images, I hope, look a bit funny to you. Let me explain why. To get an intuition for this, let's look at the rainbow-colored images in grayscale alongside the original image in grayscale. You can see that in the grayscaled rainbow map, there are dark blotches on the lady's face here, where the lady's face should be almost white. The problem here is with the luminous or lightness of this color map, which is called jet. But colors aren't all bad. Certain color maps do work. For example, this one called Batlow. When you look at it in grayscale, the contours still make sense. This is called a perceptually uniform color map. But let's dig deeper into why it's called that. First, we need to understand the difference between physical lightness and spectral lightness. So as a demo, I'm asking you which of these squares is the lightest. You might think that the green one is lighter, but they all have the same physical amount of lightness. What you're relying on is the perceptual lightness. For green, there's a big difference between the perceptual and the physical lightness. You can see the physical lightness is uniform across all these, but the perceptual lightness increases at green, which is why you probably thought green was lightest. This is because we're particularly sensitive to luminance in the green area of the spectrum. So this graph shows the changing spectral sensitivity to luminance as we go across the color spectrum. These values are from the HSL way of defining colors. H stands for hue, S for saturation, and L for luminance. It's physically accurate, but as we just saw, it's not perceptually accurate. Alternatively, we can use a palette that has been controlled for spectral sensitivity to luminance. Here the colors have the same perceptual lightness, you can see with the 50s down here, but different physical lightness. This is a palette called HS Love, or H star, S star, L star. Once a palette has been adjusted according to perception, it is called perceptually uniform. Here is a perceptually uniform color map that we saw before, derived from this kind of palette. It looks duller than the raw physical colors because some colors need to be darkened in order to match the perception of other colors. To understand this problem, we need to think about color in terms of hue, saturation, and luminance. I'm going to go to Inkscape, which is an open source vector graphic program, to demonstrate this. Okay, so here I am in Inkscape, and I've just made a square block of color, and we're looking at the HSL color wheel. You can remember, hopefully, that this is the physically accurate color map. Here we have the hue. You can systematically change the hue. Adds up to 360 because it's encoded like a circle, 360 degrees. Here we have the saturation, which is the amount of gray in the image. If we were to take all of the color out of the image to only leave gray, then we'd have an image in grayscale. And here we have the lightness, which is the amount of white and black in a color. Alternatively, we can look at the HS Love color map. Here again we have hue, but you can see that certain colors, especially in this yellow-green area, look a little bit duller because they've had their physical lightness adjusted so that it matches the perceptual lightness. And as we adjust the lightness, you'll see that the shape of which colors are available changes. So now let's see how you would make a perceptually uniform color map from that kind of palette. Here I have the original image of a perceptually uniform color map that's available in Python. This is called Viridis. And here I've taken evenly spaced instances of the color and just spelled out the hue, saturation, and lightness so we can look at them. So you can see as we move from one square to the next, if you watch this bar here, you're going to see that we're moving to the left along the hue bar. But we're also moving along the lightness bar. So the essential thing for a perceptually uniform color map is that it not only changes in hue at an even rate, but it also changes in lightness. And you can actually see this in the numbers. For the lightness, here we have 18. 18 plus 18 is 36, plus 18 is 54, plus 18 is 72, plus 18 is 90. And just to make this even more obvious, I remade this PNG, this raster-based image, as a vector graphic using the gradient option. And here you see the color at the left side. You can see the lightness is 18, and as I move along, you can see it moving across the luminance. There you go. Now we understand how a perceptually uniform color map is made, we should think about different kinds. You also need to match the type of color map to the type of data you have. So if you have ordered data, so data that has an inherent order, you can't mix up the order and have it still make sense, you should use a sequential color map. And whether you use a continuously changing color map or a more discrete color map depends on whether small differences in values are important. You should use a diverging color map if you have data that has a logical middle point. For example, it's useful for plotting things like correlation coefficients or temperature, which can be positive or negative. Finally, there's the multi-sequential color map. This kind of map is useful when there's a point somewhere in the middle or at some point where it makes sense to qualitatively separate two kinds of data. So for example, in geography, you might have depth in the ocean in blue here, and then altitude on land in green to beige here. Finally, if your data is ordered cyclically, you could use a cyclically ordered color map. For categorical data, you should use colors from a sequential color map. And just to see if you've been following, ask yourself why you would use the sequential color map as opposed to, say, the diverging one. It becomes more obvious when you look at the maps in grayscale, that is, when I remove all the saturation. If each color maps onto only one level of luminance, as it does here in the sequential color map, then the chart should be understandable in grayscale. Whereas if you're using something like the diverging color map, if you have, say, a dark gray value, you won't be able to tell whether it comes from this position or this position. Now that was a lot of information. I've created some cheat sheets for different topics so you can easily refer back. But as a rule of thumb, you can just test yourself or someone else as to what different elements of your visualization mean. So for example, you could ask someone which bar is higher, and if they don't know, you might need to change it. And I hope you've learned that it's really helpful to look at images in grayscale, that is, to remove all the saturation, in order to see if the colors still work when if the luminance matches on to the color map. And this is especially relevant if you have people who have visual color deficiencies like color blindness in your audience. And in the US, 8% of men and 1% of women have visual color deficiencies. So chances are, if you're speaking at a conference or something, somebody will benefit because of their deficiency from you using a perceptually uniform color map. So here's the cheat sheet I made for choosing effective charts. It's a busy slide because I want you to be able to see and compare all of the info at once, but we'll go through some examples to show you how to use this. On the right, we see a summary table showing which channels are most effective for expressing magnitudes and identities. So on the left here, we have channels that express magnitude, so an amount or ordered data. And on the right here, we have channels that express identity. And going from bottom to top, these different types of channels increase in effectiveness. So notice that this chart doesn't outline which channels are best for expressing higher level messages like patterns. Luminance may not be very effective for decoding exact values, as we saw in one of our demos, but it can be effective for decoding patterns and shapes. So on the left, we have different kinds of charts, and I haven't labeled them because most of you as grad students will know the labels, but you can find the labels easily on the cheat sheet for MATLAB. For Matplotlib that I'll be sharing in the next lecture. Just as a preview, this is that cheat sheet, and here are the different plots and the code you can use to create them. So we're going to go through a few of these examples and see why these different charts are effective based on what types of channels they use to communicate information. So first we have the line plot. We've seen this plot before. Now let's unpack how it communicates. Ordered values are encoded on a common scale by position. So the common scales are x-axis and the y-axis, and the values are encoded by their position on these two scales. But this kind of data is also redundantly encoded in text. So here we have a number for each line that corresponds to n in this equation, and so that's a kind of redundant encoding because you can use that number to calculate these lines yourself. You can calculate the relationship between x and y based on the number. The categorical values are encoded with color and text. Putting the text right beside the lines is very effective here, in my opinion. If they were in a legend, it would require more cognitive effort to remember the color and look up its meaning. You'd have to say, oh, okay, here's a gray line, now I have to go over here and look in this legend that says the gray line means brightness. Whereas you can just look at this very quickly and understand what each line means. It's especially relevant when you have colors that are similar, like this lighter and slightly darker green, because these colors don't map onto a perceptually uniform color map. They wouldn't be understandable in grayscale. So here we see the cheat sheet, and I've put a check mark behind beside the elements that our example used. We may know intuitively that it was a good visualization, but now we can see why, and maybe we can understand why line charts are so common. They use very effective elements of position on a common scale, and often for different channels they use color hue for different groups or identities. It also redundantly encoded both of the categories and the magnitudes with very effectively placed text. Now in the original version of this graph, they didn't have text here, but I added it because I think it can be a very useful cue. Not just as an explanation, say in a figure description, but actually in the figure itself. So here we have a bar chart. It's from the original paper for the Abide dataset, which is the dataset that we'll be using in the next tutorial, in the next lecture, when we talk about Matplotlib. They classified participants with autism using functional connectivity. So here we see the classification accuracy on the y-axis for different scales of connectomes in this legend here, and for different sites where they collected the data. For the ordered variable of accuracy, they used position on a common scale. And for the categorical variable of site, they used spatial regions. So this region of bars is physically separated from this region of bars, and that's also a very effective channel for communicating groups. But let's think about the final variable. They've encoded in hue these categories of what threshold was used to determine which connections were kept in the connectome. Hue is used for categorical variables, but you can see that this, if we think about it a little more deeply, we can see that this is actually an ordered variable. And this becomes even more obvious that their colors aren't effective when we see them in grayscale. They essentially used a diverging color map, but the values don't have a logical center point. So here's the cheat sheet, and I've marked which elements they use correctly, the position on a common scale and the spatial region, and which are perhaps misleading. The color hue was used for the categorical channel of color hue was used for the magnitude channel for ordered attributes, but they didn't redundantly encode it with color luminance. That is, they didn't use a sequential color map to choose the colors, so it's a little bit misleading. We can improve this by using luminance to encode the variable as an ordered variable. So let's focus on the chart a little more and see what else we can improve. So here I've changed the colors so that they follow that Viridis color map that I showed a few minutes ago. To make the colors and values are the same, but I've reordered the bars so that the number of connections increases towards the right. Previously, they were increasing towards the left, which is rather counterintuitive for the way we're used to seeing charts. Oh, there we go. We can make this even more obvious by rotating the legend and including more explanatory text. With things aligned in this way, there's a trend that becomes more obvious. The accuracy tends to decrease as we increase the number of connections. We could make this even more obvious by including trend lines. These aren't calculated, I just kind of estimated where they would go. And further, we could use the figure title to explicitly state our message. So we could explicitly say that across locations, the diagnostic accuracy is fairly consistent, around 55%, so you can see that very quickly from the figure, that these bars don't differ too much. Further, the diagnostic accuracy tends to decrease as we include more connections in the connectome. And you can see that there. So next I have a cheat sheet for choosing color maps. It's pretty easy to follow, so I'll let you try that when you need to. I just stuck this on there to remind you with humor, so hopefully you remember it, to stop using jet as your color map. And you can always, once you know which color map you need, you can go onto the matplotlib documentation in order to choose a specific one that's available. So here you see the Viridis color map, which we were looking at before. We've just seen some ways of visualizing data that are more effective based on perceptual evidence, but we also need to consider conventions that could influence our design choices. As a really basic example, consider cultural color associations. In Western culture, we associate pink and blue with male and female respectively. If we make a visualization where this color coding is backwards, it might take more cognitive load for the viewer to understand it. We've already talked about rainbow color maps, but I just want to emphasize that some people have really strong opinions about it. This person says, does anyone else have a visceral negative reaction when they see the jet color map? And I personally do, so I can relate to this. This person ran a poll, non-scientific one, just on Twitter, where they found that about a quarter of respondents indicated that if they were reviewing a paper, they would instruct authors to change their color map from jet to a perceptually uniform color map. On the other hand, there is a rainbow map that is perceptually uniform. It's a diverging color map called turbo, and this is shown here. And like this person says, it's great news for someone who likes having nameable colors. So they want to be able to say, look at the red region, look at the blue region, and have listeners easily follow what they're saying. But I would be wary about using rainbow color maps because even if it is perceptually uniform, it still looks a lot like jet, and people have really strong opinions about jet. In neuroscience, we have this convention that colors can represent three-dimensional directions. So this is a map of the principal diffusion direction of water in the brain, which roughly shows white matter tracts. And the 3 dimensions are represented by red, green, and blue. And here's a more complicated mapping of the color onto dimensions. So this mapping is not intuitive and the color choices are arbitrary, but if everybody visualizes diffusion directions in this way, then people might get good at understanding these maps without too much cognitive effort. Personally, for me, I'm not in this field, so for me, it takes a while for me to wrap my head around something like, what does yellow mean in this kind of map? So basically, you might want to use this kind of visualization, even if maybe it's not an ideal mapping of a property like direction onto a visual property like color. So here's a summary slide for future reference. I think it's easy to understand. The important thing is just to think about it. So we'll move on. Finally, we'll touch on how visualizations should be adjusted according to where people will see them. There are basically 3 places where we see data visualizations in academia: presentations, in posters, and in papers. I'd argue that these have a rough order, moving from left to right, in how self-explanatory they need to be. For example, a presentation slide does not need to be self-explanatory. In fact, it should be very simple. You should ask yourself, how long would it take them to understand this slide, and how long will they see this slide? So personally, with this figure here, which I took from the paper example in the previous slide, I would say it would probably take about 5 minutes for me to understand all these charts and read this figure legend. But the presenter probably won't let me see it for 5 minutes, so they should have made a more simple slide. Here's another example where I take a figure from a textbook and I adapted it for a slide in this presentation. So I increased the font, I selected only part of the figure, and I added annotations to help people understand it quickly. Basically, you should adjust figures according to how much time people will have to understand it and how close they'll be to the figure. So that's time to understand and proximity to the visualization. This will inform how much text explanations there should be, how self-explanatory it should be, and how visually complicated it should be. Now that we've discussed all these principles, we're going to plan a simple figure to drive these points home. We'll use a tiny bit of data from the Abide dataset, which we're going to be using more extensively in the next tutorial and lecture. And we'll simply use the number of males and the number of females in the dataset. So what's our message? There are more males than females. There are and if we abstract this, we see there are 2 categories and 2 values. How should we communicate this? Well, a bar chart clearly shows 2 categories and 2 values. And we could just leave it at this. This is a perfectly understandable figure. But let's keep going just to illustrate how the different steps would influence the figure. So here's the cheat sheet I made for choosing an effective chart. Again, it's a busy slide, but let's consider what to use here in our other visualization. So we've encoded the number as positions on a common scale, which is very effective, and we've encoded the identity of the 2 groups in spatial region, which is very effective. If we wanted to redundantly encode things, we could encode the identities in color or hue, and or the actual values in color luminance. So here I've done this. I've redundantly encoded the values with luminance. And here I've added color. So these 2 colors vary in both their hue and their luminance to emphasize both the different groups and the different values. However, if we're considering are there any conventions we should think about, we should probably switch the colors so that blue is male and pink is female. Not because I necessarily think this is a good convention, but just because it'll facilitate understanding of the figure. Finally, if we should think about how to adapt it to the context. If we're presenting this at an academic presentation, we should increase the font and perhaps also change the figure size to accommodate the larger font. Because it's an academic presentation, we might be able to simplify the text even more, which will save the viewers the cognitive effort of viewing all the text. So in academia, usually N represents the number of participants, and we can understand pretty easily that M is male and F is female, especially if the person is standing beside the slide talking about it. So now we've finished part 1 of Intro to Data Visualization, where we considered what we need to consider about how people decode visualizations. We need to know what we want to communicate it, how best to communicate it, how it's usually communicated, and where it will be seen. In the next lecture, we'll discuss how to encode figures that follow these principles. And that is it.